Hi, Physics 2. This is Mr. Janowski. I think this is the fourth part of the Chapter 32 slides. I don't remember. It's some part of the Chapter 32 slides. So anyhow, the do now questions. How do you figure out one side of a right triangle if you know the other two sides? Pythagoras. Yeah, if you know, two of the sides of a right triangle, Pythagoras gets you to the third side. How do you figure out one side of a right triangle if you know one side and an angle? That would be trigonometry. So SOHCAHTOA, those things. And how do you figure out one angle of a right triangle if you know two of the sides? Well, that would be inverse trig, which, again, is just part of trig. But that's how that works. So yeah, this chapter, you do a lot of these things. You've got to figure out, you've got to do step zeros and step ones and figure out components and all these things. So yeah, lots of Pythagoras, trig, and inverse trig. So to review, how do you express the angle in angle notation? You go from the positive right axis, the positive x-axis, and you measure counterclockwise. So you go around this way. So the angle we're looking at here, you could call this 315 degrees. That would work. So positive 315 degrees. Or you could call it negative 45 degrees if you want to go the other way. That works too. But what you can't call it, because that's not the convention, is 45 degrees. It could be negative 45 degrees. It could be positive 315 degrees, but it ain't 45 degrees. And then question 5. Well, you're not going to be able to answer this because you're not here. I'm recording this. On a scale of 1 to 10, how comfortable are you with unit vector notation and angle notation? So hopefully as you're doing these problems, you're getting more and more familiar with it. My advice is, go slowly, go deliberately. Keep making step zeros and step ones. And remember how these things work and how you've got to switch from one type of notation to the other. And then sometimes you have to switch back again. It's a little tedious, but it's not that hard if you keep making the sketches and the step zeros. So here's a new idea. This is Michael Faraday, the wonderful Michael Faraday. So he developed the idea of an electric field E, and that should have a hat on it, but slides doesn't let me do that. And E has units of newtons per coulomb. So here is your formula for E, the electric field, due to a point charge Q. E is equal to K times Q divided by D squared. So your distance from that point charge squared. So there's that. Here's this slide. Same thing. E with a hat. There should be a hat. For electric field, units are newtons per coulomb, and it's a vector. Yeah, over here it has the hat. It's a vector. So conceptually, Faraday's idea is a little bit different than Coulomb's idea. So here's Coulomb's law, which gives you the electric force between two charges separated by some distance d. According to Coulomb's law, if you have two charges, each charge exerts a force on the other charge. Okay, that makes sense. If you're doing Faraday's idea, you don't think of it that way. It may be the exact same thing happening, but you think of it differently. According to Faraday's idea, you imagined one of the charges as having an effect on the space around it. So that charge is having an effect on empty space. And if you bring another charge into that space, it is the space that is having the effect on that new charge, not the original charge itself. So, yeah, conceptually, it's a little weird. Philosophically, I should change that word to conceptually. It's not really philosophical. It kind of is. It's more conceptual. Whatever. But yeah, this is a little bit weird. So, does a charge change the space around it, even if there's no other charge to feel that change? If a tree falls in the forest and no one's there to hear it, does it make a sound? That kind of thing. So Faraday's contemporaries did not like this idea. They would rather have thought of everything Coulomb's way. But it has since proved to be a very, very useful way of thinking about what's going on with charges and electrostatics and things like that. Electric fields in general, ended up being a very important idea in physics. So if we're looking at these two formulas, notice how the right sides of the equal sign look so very, very similar. You have to be careful that you don't confuse them. They are very similar. It can be difficult. So to quiz you, what are the units of E? E has units of newtons per coulomb. So you can think of E, electric field, as being the force per unit charge, but there's a catch. You have to be very careful about this. Here is the catch. In the top formula, the first one we learned, that gives you the electric field created by the charge Q. So the Q in that formula is the charge that is causing the electric field. If you're looking at the bottom formula, E is equal to F divided by Q. Q means something different. This is now the charge that is experiencing the electric field that's already there. So Q in the top equation is causing an electric field. Q in the bottom equation is experiencing an electric field that is already there. So be careful when you're picking your equations that you understand what Q represents in these two equations. So electric field, it moves away from positive charges. So if you're looking at the image on the left, maybe this is a proton, and these are the field lines being caused by the proton. You can think of the electric field lines as being pushed out from the positive charge. Whereas if you look at the image on the right, this is a negative charge. Notice the arrows are going in. So you can think of a negative charge as pulling field lines into it. So how do you figure out which way these lines should go? One way you can do this is to imagine a small positive test charge. So it's a positive charge. It is small, meaning, yeah, it's a positive charge, but it's not going to cause a big effect on the existing electric fields. It's going to feel the field that is there, but it's not going to have a big effect on, it's not going to really create its own fields. That's what it means to be small in this case. So if that positive charge, that small positive test charge that you bring near into this field, whichever way it's going, that is the direction of the field lines. So if you're looking at these two pictures, fairly straightforward. Things are just going radially out from the one on the left, and they're coming radially in on the one on the right. It can get much more confusing than that. When you stop having just single point charges and you start having multiple charges, possibly of opposite signs, possibly of the same signs, possibly opposite signs but different magnitudes, and maybe you're bringing conductors. So these weird shapes, this rectangle, this kidney shape, and this other curvilinear thing going on here, these are like solid conductors. They have a weird effect on electric field lines. We'll talk about that later. But yeah, so it can get complicated. So that's it for today's part of the slides. Hopefully you found that helpful.